Alright, so today we're going to talk about graphing absolute value equations. I'm going to show you a couple of different ways to do this. Some are easier and some are harder. But first I want to talk about the parent function. So a parent function is the original. Okay, just like your parent is the original of you, a parent function has no transformations, no movement of any kind around the x and y coordinate. So the parent function of an absolute value is f of x is equal to the absolute value of x. Okay, so in order to graph this, what you can start with is an x and y table. Okay, so if I just start plugging in some random numbers into this table, so let's plug in -2. What I'm going to do is I'm going to plug in -2 in for x in the equation. Well, the absolute value of -2 is +2. So that means that my coordinate point is -2, 2. So over here on my graph at -2, 2, I have a coordinate point. Okay? And I can do this a few more times. Let's plug in 0. I have the absolute value of 0, well, that's just 0. So I have a coordinate point there. Let's plug in +2. The absolute value of +2 is 2. So I have a coordinate point there. So now we can draw a sketch of what this graph looks like. And all absolute value graphs are gonna be a V shape, okay? So this is the graph of the parent function. We will use this to find various transformations. So now I want to talk about what happens whenever we start manipulating the parent function. So if you look at this first one, f of x is equal to the absolute value of x plus 2. We can plug in some random values in for x and see what we get out for y. So let's say I'm going to plug in -2. So that would mean that I have the absolute value of -2 plus 2, which the absolute value of -2 is 2, so I get 4. So I have a coordinate point at -2, 4, which is right about there. If I plug in -1, have the absolute value of -1 plus 2. The absolute value of -1 is +1, so I get 3. So my coordinate point is -1, 3. Let's plug in 0. So absolute value of 0 is 0, plus 2 is 2. So my coordinate point is 0, 2. Let's do one more. Let's go ahead and plug in 1. Absolute value of +1 is just +1, plus 2 is 3. So my coordinate point is at 1, 3. So you can draw your graph here, and it would help if I had a ruler, but I don't. And it makes a V. Now if you compare this to the parent function, it shifted up 2, okay? And that's because of this guy right here, okay? If I look at this second one here, f of x is equal to the absolute value of x minus 3, where the -3 is inside of the absolute value. Again, let's plug in some points. Let's plug in, we'll do -1. So you would have the absolute value of negative 1 minus 3. Now this is all inside absolute values, so that gives you the absolute value of negative 4, which is positive 4. So at negative 1, we are at positive 4. If I plug in 0, I will get 0 minus 3, all in absolute values. That will give me the absolute value of negative 3, which is positive 3. So my coordinate point is 0, 3. Let's plug in, let's see here. Let's plug in 2. If I plug in 2, I get 2 minus 3. So that gives me the absolute value of negative 1, which is 1. So at 2, I am at 1. And one more, I'm going to plug in 3. Actually, we might do 2 more. So 3 minus 3 is 0. The absolute value of 0 is 0. So my coordinate point is 3, 0. One more, let's do 4. 4 minus 3 is 1. The absolute value of 1 is 1. So your coordinate point is 4, 1. So you want to find that where it bounces back up. So if you connect the dots here, you will see that you have another V graph. Now compare this one to the parent function, and it shifted to the right 3. And that's because of that guy right there. Couple more that I want to show you. What happens whenever we have a number being multiplied on the outside? So let's take this first one for example. 2, absolute value of x. So let's say I'm going to plug in negative 1. I will get 2 times the absolute value of negative 1, which is just 2 times positive 1, which is 2. So at negative 1, I am at 2. If I plug in 0, 2 times the absolute value of 0, well, that is just 2 times 0, which is 0. And let's plug in 1. So 2 times the absolute value of 1 is just 2 times 1, which is 2. So if you compare this graph to the parent function, you'll notice that it's a little skinnier, okay? And that's because of this 2 here, okay? We call this a stretch, okay? And last but not least, let's look at what happens whenever there's a negative out front. So if I plug in, let's say negative 1, I have negative absolute value of negative 1. Well, that's the absolute value of negative 1 is 1. So my answer is negative 1. So on my graph, negative 1, right there. If I plug in 0, negative absolute value of 0, well, that's just 0. So my coordinate point is 0, 0. One more. Let's plug in 1. Absolute value of 1 is positive 1. Slap that negative on it, and you get negative 1. So if you notice, now my graph is flipped upside down. And that's because of the negative out front. Okay, so now that you've seen some examples with some transformations happening, I want to show you the basis on how we know what transformations are happening. So we have this function here, y equals a times x minus the absolute value of x minus h plus k. And each of those letters do something. So a, which is being multiplied by that absolute value, that tells you whether it is a stretch or a compression. So if it is a stretch, that means that your a is bigger than 1. Okay? If it is a compression, then your a is between 0 and 1. Okay? Now, something interesting happens whenever your a is negative. So if a is less than 0, which means that it's negative, then you have what we call a reflection, where it flips over. Okay? So that's what the a does. The h is your horizontal shift, whether it moves left or right. Okay? Now this one's kind of tricky to figure out because inside of the absolute values you have that minus sign. Okay? So we are going to pretend that that minus sign is part of, you see how it's in white? It's part of the basis of this equation. We are only going to look at the h. Okay? So if your h is positive, which means that it's bigger than 0, you move to the right. If your h is negative, then you move to the left. Okay? Now, if it is to the right, you will have something like the absolute value of x minus a number. If it moves to the left, you'll have something like x plus a number. And the reason why is because that negative h value is it's that double negative. So minus a negative turns into a positive. Okay? The k value, that's your vertical shift. Okay? So if this one's really easy, if k is positive, you go up. If k is negative, you go down. All right? So the way that you can graph these absolute values without having to make a table is knowing what transformations are happening. Okay? So let's take this example here. Y equals 2 times the absolute value of x minus 1 minus 3. So this 2 here means that it is a stretch. The a is bigger than 1. So imagine a rubber band that you're stretching. Okay, it's going to get skinnier. The h is just the 1. Okay, so remember, this one can be tricky to find out. The h is 1, so it is positive, so it moves to the right. Your k is the negative 3. You take the sign with it. So this means that you move down. Okay? So on my graph here, I have already plotted the vertex, which is the bottom of the v of the parent function. Okay? The vertex of the parent function is at 0, 0. So without having to make a table, I can start to move this vertex based on some of the transformations that I see happening. So what I'm going to do is I know that this vertex is going to move right 1. So I'm going to take it and put it right there. Okay. Now I know that this vertex is going to move down 3. So I take that one, 1, 2, 3, and I'm going to put it right there. Okay, so your vertex now is at 1, -3. Now we have this stretch. The way to calculate the stretch, and it only works with absolute values, is it acts like a slope. So from the vertex, if I have a slope of 2, that means I'm going to go up 2 and over 1. So there's my second point. Now, because an absolute value is symmetric, which means it's the same on both sides, I can cut it in half and it'll be the same. I can go up 2 and to the left 1. Now I can sketch my graph. And that is the graph of y equals 2 absolute value of x minus 1 minus 3. Okay, so this is a little bit of extra information. You have already learned how to solve absolute value equations and to get solutions. So I want to show you what those solutions actually mean graphically, okay? So before, we've learned to solve absolute values by getting the absolute value by itself. Okay, divide by 3. Then I make my two equations. So one where it equals a positive 3 and one where it equals a negative 3. Oops. Then I solve, so I subtract 2 on both sides. So these right here are my solutions, okay? Now, I want to show you what this means graphically. So if I were to take each side of that equal sign and make its own equation, so that means that I would have one equation, which is y equals 3, absolute value of x plus 2 minus 1. And then the other equation is y equals 8. Okay? If I were to graph those two equations separately, you'll see where those two will intersect. Okay? So let's graph this absolute value one. I'm going to use red. So this guy right here, because it's x plus 2, that means that it shifts left and down 1. Okay, so from the origin here, you are going to go left 2 and down 1, and that's going to be your vertex. This a value here tells you that it's a stretch, so remember it kind of acts like a slope. So from this vertex, you can go up 3 and over 1. Okay, and you do that both ways, and you get this graph here. All right, I know it's not perfect, but we're gonna work with it. So now I want to graph this line y equals 8. This is a horizontal line, okay, and it will cross the y-axis at 8. So right up top here, that's my second graph, or my second line, okay? And if you notice, where these two lines cross, those are your solutions. Okay? Now if I had graph paper, it would look so much cleaner, but they do intersect at x equals 1 and x equals -5. Okay, so this is what it means to have solutions. It's where the two graphs cross.